Hi dear friends, myself Bhavsai Sononi, Assistant Professor in Department of Chemistry, Gokhale Education Society's Arts, Commerce and Science College, Jawar, District Palghar. Dear friends, in the previous all parts of the video, we have completed two topics, particularly nuclear chemistry, and after the nuclear chemistry, we also studied about surface chemistry. Dear friends, after the completion of these two topics, now we are going to discuss about the another new topic entitled as chemical kinetics. Definitely this topic is much more familiar to you all because you might have studied this topic in your 11th, 12th as well as F5 BSc, S5 BSc, and now it is also here it is in the last year also we are going to talk about the same topic, chemical kinetics. In the chemical kinetics, particularly we are discussing about the rate of reaction, factors affecting rate of reaction, order, molecularity, and various parameters which are responsible to decide the rate of reaction. Dear friends, in this part of the video, as we are going to talk about a chemical kinetics, but here we will study this chemical kinetics particularly for the gaseous reaction in which the rate of reaction depends upon the collision between the molecule. So how the collision between the molecule decide the rate of reaction or it affect the rate of reaction, that we will discuss in this part. So today we are going to start our new topic, chemical kinetics, with the study of collision between the two molecules which are responsible for the rate of reaction, and how the collision between the two molecules or how the molecule behave during the collision between them is explained with the help of a particular famous theory which is entitled as collision theory. So dear friends, today in this part of the video we are interested to discuss the rate of reaction with the help of collision theory, and this collision theory particularly applicable to gaseous reactions or the gaseous molecule. So what are the assumptions of this collision theory? Because with the help of these assumptions of collision theory we are also able to derive the equation for rate of reaction or the rate equation for the gaseous reaction. Here this is the first assumption stated by means of an collision theory is that the molecules generally treated as the rigid sphere which describes only the translational motion. So according to the collision theory, the molecules are treated as a rigid spheres and which shows the only translational motion. Again, these rigid sphere molecule also collide or they must collide for the reaction to take place or for the reaction between them. So this reactant molecule, rigid sphere reactor molecule, must collide in order to give the product, in order to react. So if and only if the molecule will collide, then and then the reaction is possible, otherwise the reaction will not possible. So collision is must for the reaction between them to give the product. So again, the another assumption stated by means of this collision theory is that during the collision there is always exchange of energy from one molecule to another molecule, but and no gain or loss of energy of molecule, and such a collision in which the exchange of energy take place but no net gain or the net loss of energy take place between the molecule. It means that the total energy of the molecule remains constant, remains same, and such collisions are called as elastic collision. It means that if we consider the energy of the molecule before and after collision, it will remain same, then such collisions are called as elastic collision. Again, this is very important in order to decide the rate of reaction in the gaseous molecule, and this is a number of collision. So this number of collision between the molecules treated as a rigid sphere can be calculated with the help of theory, and this theory is called as a kinetic theory of gas, because this is the only theory or this is the most important theory which can explain the behavior of gas molecules. And that's why whenever we want to calculate the number of collision between the gas molecule or between the molecules which are treated as the rigid sphere, for that purpose we can use the kinetic theory. So number of collision between the molecule can be calculated with the help of kinetic theory of gases, and this number of collision later on will decide the rate of reaction. What is the relationship between number of collision and the rate of reaction, or how the number of collision will be used to calculate the rate of reaction, that we will discuss later on with the help of equation. The another assumption stated by Mr. in this collision theory is that during the collision some molecule may gain or others may lose energy, but the total energy remains constant. But the total energy of the molecule remains constant. So during the collision, it is possible that they can exchange the energy between them. So some molecule can gain and others can lose the energy, but the total energy of the system, or the total energy of the molecule, of all the molecule, will remain constant, just like the elastic collision. And only those molecule which possesses energy above certain minimum value, above certain minimum limit, will react on collision, and such collisions are called as effective collision. So it's very important. So how many energy, or so how much energy the molecule has after the collision, and that value must be above certain minimum value, that generally we call it as the energy of activation. So energy of the molecule after collision must be equal or greater than the energy of activation. Then and then the molecule is able to react, and such collisions which are having energy above certain minimum value are called as effective collision. Definitely after the number of collision we came to the another term, it's called as effective collision, and effective collisions are the collision which will have the energy above certain minimum value is called as effective collision. And for effective collisions, the molecule must have suitable orientation or the proper orientation. It's very important. If the molecule has to react on collision, so that it must has to acquire energy, or it must have energy above certain minimum value, and for that the molecule must be suitably oriented, or it must have proper orientation during the collision. Then and then this collision will be called as effective collision. And when the molecule take part in effective collision, it's very important, a reactant get converted into product. It means that whenever the molecule take part in effective collision, it means that it is going to react. It is going to react, and it will be responsible to form the product. And during such a process, a rearrangement of bonds take place in the reactant molecule, resulting in the formation of product. It's very important. So if the molecule take part in the effective collision, it means that the collision of the molecule has sufficient energy, or has energy above certain minimum value, then it will be responsible to form the product. And during the formation of product, rearrangement of bonds take place in the reactant molecule, resulting in the formation of products. Another assumption which is very important to decide or to determine the rate of such a molecules involving the collision, or such a reaction involving the collision between the molecule. And according to the collision theory, rate of reaction is simply directly proportional. Rate of reaction is simply directly proportional to the number of collision per unit volume per unit time. How many collisions take place per unit volume per unit time? That number of collision per unit volume per unit time is directly proportional to the rate of reaction. It means that if the number of collisions are more, rate of reaction will be also more. And here, not only the number of collision, but the number of collision per second per cubic centimeter, number of collision per second per cubic centimeter in any gas is given by the kinetic energy. So just as said here, rate of reaction is directly proportional to the number of collision per unit volume per unit time, and this number of collision per second per cubic centimeter can be calculated with the help of kinetic theory of gas. And this number of collision per second per cubic centimeter is simply given or is calculated with the help of collision, is calculated with the help of kinetic theory, and it is simply given as z is equal to 2 into n square into sigma square into under root of pi r into t divided by capital M. So what is this? Actually this z is the number of collision. Try to understand. This is the number of collision. Number of collision per cubic centimeter per second is simply given. So these are the number of collision between the molecule, and this number of collision 2 into n square into sigma square into under root of pi r into t divided by m. So what are the meanings of all these terms which are involved in this equation of the number of collision with the help of kinetic theory of gas? Here this n is simply the number of molecules per cubic centimeter. Sigma is the collision diameter of the gaseous molecules which are going to collide with one another. R is the gas constant. T is the absolute temperature at which the collision between the gas molecule take place. And M is the molecular weight of the gas in which the chemical reaction is going to take place, in which the chemical reaction we are going to study, or in which the rate of reaction is to be calculated. Another assumption or the thing is given by means of this collision theory. The number of collisions or the number of colliding molecule per second per cubic centimeter will be twice the Z, or will be twice of the Z. It means that for biomolecular reaction, it means that if one collision take place, but for the one collision we will require the two molecules. It means that if Z is the number of collision, then the number of molecule colliding per second per cubic centimeter will be twice. So here definitely for one collision, as we are requiring the two molecules, so definitely the number of collision will be half of the number of molecule, or number of molecule will be twice of the number of collision. So number of molecule colliding per second per cubic centimeter will be twice of the Z, because Z is the number of collision, and that's why the number of molecule colliding with one another in biomolecular reaction will be twice of the Z, twice of the number of collisions. And suppose instead of a pure gas, we have provided here a mixture of gas in which the two gases are present as gas 1 and the gas 2. Then in this mixture of the gas containing the two gases, the number of collisions suppose indicated by Z12 take place per second per cubic centimeter is simply given by, if the gas containing the mixture of the two gases, then the number of collision is simply given by Z. 1 in 2 indicates the mixture of two gases, so number of collision for the gases containing number of collision in the mixture of the gases containing gas 1 and 2 will be equal to n1 into n2 into sigma 12 square under root of 8 pi r into t into bracket m1 plus m2 divided by m1 into m2. What are the meanings of all this? Here n1 and n2, definitely this indicating the number of molecules of two gases, gas 1 and gas 2, in gas mixture in which the chemical reaction is going to take place due to the collision between them. So n1 and n2 indicates the number of molecules of gas 1 and gas 2 respectively. Sigma 12, this is the average molecular diameter, because it is not possible to measure the exact diameter of the molecule. So as the two gases are involving in this, so here the sigma 12 is the average diameter of molecule of gas 1 and the molecules of gas 2. Means sigma 1 is the diameter of gas 1, molecules of gas 1, and sigma 2 is the molecular diameter of molecules of gas 2, and their average is indicated by means of sigma 1 2. It means that suppose this is the 5.5 and later it is nothing but the 6.5, then the average of this will be called as sigma 1 2. And m1 and m2, these are the molecular weights of the gas 1 and the gas 2 respectively. So dear friends, in this part we have discussed about the collision theory, which is very important to explain the rate of reaction in gaseous reaction with the help of due to the collision between the gas molecule. So I think in addition to the previous part, this is now extended part of the chemical kinetics, in which we have studied about the rate of reaction with the help of collision theory, particularly in gaseous reaction. So how we can explain the rate of reaction in gaseous reaction with the help of collision theory, because there are some assumptions stated by means of in collision theory which are very useful to determine the rate of reaction or rate equation in the reaction involving gas molecule. So dear friends, in the next part of the video we will discuss about how the rate equation can be calculated, or how the rate equation can be derived for such type of the reactions, such type of the gaseous reaction which are explained on the basis of collision theory. So thank you very much. We will resume in the next part of the video to discuss the rate equation for such type of the gaseous reaction on the basis of collision theory. So thank you very much.